Okay, now we'll talk about glucose. Biomedically, glucose is the most important monosaccharide. So it is most important monosaccharide biomedically, right? There are three ways to represent it, glucose. To represent glucose, the first one is straight chain structure formula. Chain structural formula, or aldose-ketose, right? That is HC double bond O, HCOH, CHOH, HCOH, COH, H, and CH2OH. This is the first way we can represent glucose. This is a straight chain structure formula, or aldose-ketose structure of glucose. Second is cyclic structure. Cyclic structure is also called hemiacetal. And it is formed by reaction between aldehyde group and hydroxy group. This is thermodynamically favored. And this explains the properties of glucose, which cannot be explained by the straight chain structure formula. So the structure is this is hemiacetal. And the last method to represent glucose is the Haworth projection. This is also called chair form. CH2OH, H, H, OH, OH, H, OH, H, H, OH, right? This is also called chair form. Now we'll talk about the isomerism of carbohydrates. So we'll be talking about isomerism in sugars. Okay, more specifically in glucose. So glucose has 4 chiral carbons and can represent 16 isomers. Here we will talk about the important ones. First one is D and L isomerism. Right? D and L isomerism. So this isomerism is based on a naturally occurring monosaccharide, which is glyceraldehyde. The 5th carbon atom of the glucose is compared with the 2nd carbon atom of glyceraldehyde, and accordingly D and L forms are understood. First I'll draw glyceraldehyde, D-glyceraldehyde and L-glyceraldehyde, and below them I'm going to draw glucose D and L, by which you can compare both structures. Here we have L-glyceraldehyde. This is L-glyceraldehyde, and here we will have D-glyceraldehyde. This is D-glyceraldehyde, right? Now below them I'm going to draw L-glucose and D-glucose. This is right? This is L-glucose and this is D-glucose. How can this be compared? Look here. 1, 2, 3, 4, 5, 6. This is 5th carbon. Here 1, 2, 3, 4, 5, 6. This is 5th carbon. Look at the direction of H and OH on the 5th carbon. Here again you have 1, 2, 3. 1, 2, 3. Look at the position of H and OH on the 2nd carbon, right? According to that, glucose is designated as either D-glucose or L-glucose. So most of the naturally occurring monosaccharides are D sugars, right? Most naturally occurring monosaccharides are D sugars. So D-glucose is more common. And why is it so? Because enzymes responsible for data metabolism are specific to this configuration. Enzymes are specific to this configuration. Next kind of isomerism we are going to discuss is optical isomerism or optical activity. Optical isomerism. Here we designate glucose either as a D plus or D plus or L minus, right? That is dextrorotatory, which is plus, or levorotatory, which is minus. And how is it so? Well, this depends upon the direction of rotation of polarized light. When polarized light is incident on these sugar solutions, either it will be rotated towards the right or towards the left. The sugars which rotate the polarized light towards the right are called dextrorotatory sugars, and the ones which rotate it towards the left are called levorotatory sugars. right? Since in solution, sugar that glucose is dextrorotatory, so it is often called as dextrose, whereas fructose is levorotatory. Next we'll be discussing about Pyranose and Furanose ring structures. In more than 99% solution, glucose occurs in pyranose form, and furanose is present about 1%. Right? This is pyranose. And furanose. Furanose will have a 5-membered ring, whereas pyranose will have a 6-membered ring. This will have a 5-membered ring. Next we are going to talk about alpha and beta anomers. Right? Alpha and beta anomers. So what is anomeric carbon? This is the carbon which has carbonyl group. In glucose it will be carbon number 1. In fructose it will be carbon number 2. In ring structure, aldose is present as hemialdose, whereas ketose is present as hemiketal. Right? Aldehyde group will be as hemiacetal, and ketone group as hemiketal. Right? Talking about fructose. In fructose solution, alpha glucopyranose is about 38%, beta glucopyranose is about 62%, and less than 0.3% is present as alpha and beta anomers of glucofuranose. Right? Now we'll be drawing pyranose and furanose forms of glucose, of fructose, sorry. We're drawing only pyranose forms because fructose are quite rare and quite out of context. Just to give you a brief introduction to the Enomerism. Here is alpha D fructopyranose, and here we will have beta D fructopyranose. OH, 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 and OH. Now what's the difference in both these structures? This is this group. Carbon number 2, CH2, OH, whereas here it will be OH, CH2, OH. This is carbon number 2 here, carbon number 2 here. Right? So this is alpha G fructopyranose and this is beta G fructopyranose. Now the next thing we are going to discuss here are epimers. Epimers are those isomers which differ in configuration of H and OH on carbon numbers 2, 3 and 4. Important anomers of glucose are mannose and galactose. Mannose is a glucose epimer at carbon number 2, whereas galactose is a glucose anomer at carbon number 4. Right? So this is alpha D glucose. Here we will have alpha D galactose, and here we will have alpha D mannose. Right? Let's do the numbering. 1, 2, 3, 4, 5, and somewhere around this we will have 6. CH2OH, CH2OH, CH2OH. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Right? So here glucose will have OH, 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 and OH. Right? Galactose differs from glucose in the position of H and OH at carbon number 4. So carbon number 4 will have OH. Let me draw it with different color. OH. Right? Then here you will have OH, OH, and OH. Whereas mannose differs at carbon number 2, so it will have OH, 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 and OH. Right? These are anomeric forms of glucose. Sorry, epimeric forms of glucose. Next is aldose-ketose isomerism. Right? So this is shown between fructose and glucose. How is it so? They will have the same structural formula, but fructose has a ketone group at carbon number 2, whereas glucose has an aldehyde group at its first carbon. Now we exploit a special property of aldehydes here in a test. Chemically, aldoses are reducing sugars. Right? Or they are reducing compounds. So this provides a basis for the chemical reaction test for glucose in urine in poorly controlled diabetes mellitus. What will happen if a person has a poorly controlled diabetes mellitus? So blood glucose level will rise. That will lead to a rise in glucose or sugar in urine. Naturally, sugar is not found in urine. So a simple chemical test can be done to detect this. That is reduction of an alkaline copper solution. Reduction of an alkaline copper solution is used for detection of sugar in urine in case of poorly controlled diabetes mellitus.